All right, y'all. Today we're going to be talking about systems of three equations. And the key difference between systems of three equations and system of two equations is not just that we have three equations still with two variables, but we actually have three equations with three variables. And so that adds an extra level of complexity to solving them and finding those solutions. But it's going to build off of those skills we've used for systems of two, that elimination, that substitution. Can't really do graphing for this one since we have an x, y, and a z variable. That would be pretty challenging to graph, but we can use our elimination and substitution skills. Okay, so let's look at the one that we have here. We have equation 1, x plus y plus 2z equals 3. Equation 2, 2x plus y plus 3z equals 7. And equation 3, negative x minus 2y plus z is equal to 10. So we have three equations with three variables. And what we want to do is we're actually going to start off with elimination, and we're going to do elimination twice with two sets of equations. And our goal with this elimination is to get not just a variable to cancel out, but the same variable to cancel out with both sets of equations. So looking at our variables, we have that y and y, which is the same coefficient, but just the same sign. So I can actually multiply one of those by -1 or just treat it like I'm subtracting and get that y to cancel out. So taking that equation 1 and that equation 2, if I multiply equation 1 by a negative, that gives me negative x minus y minus 2z equals -3. And then adding them together, that negative y and positive y are going to cancel out, leaving me with 1x plus 1z is equal to 4. And I'm going to go ahead and label that equation 4. You might be wondering why we have all these labels, is to help us keep track of these equations as we work through them. So that's our first equation. Then going back to our sets, we have that equation 3, that negative x minus 2y plus z equals 10. I could actually use either equation 1 or equation 2 to add to it. Let's take equation 2. Okay, and once again, I have y and 2y, one's positive and one's negative. So they're opposite signs, but the coefficient's not the same. So I'm going to multiply equation 2 by 2, which gives me 4x plus 2y plus 6z is equal to 14. Adding those two equations together, 2y and negative 2y is going to cancel out, leaving me with the new equation 3x plus 7z equals 24. And we're going to go ahead and label that equation 5. So our first step is doing those two sets of elimination, which gives us two new equations, but the key being that those two new equations only have two variables and they have the same two variables. So they both involve x and z. If one was x and z and one was z and y, that wouldn't be useful for us. We want them to involve the same two variables. So once we have those two equations, we're going to treat them as a new set of two equations. Then we're going to solve them like any other system of two equations. Once again, we can do substitution or elimination. I think it's easy just to stick with elimination. So x plus z equals 4 and 3x plus 7z equals 24. If I multiply equation 4 by -3, I can get those x's to cancel out. So negative 3x minus 3z equals -12. Adding those two equations together, the negative 3x and 3x cancels out. And I'm left with negative 3z plus 7z, which gives me 4z, and negative 12 plus 24, which gives me positive 12. So if I've done everything correctly, I'm doing three sets of elimination. I'll end up with a single variable equal to a single constant. So from there, I can just solve from that variable, divide both sides by 4, and we get z is equal to 3. Once I have that first variable solution, then I can start back plugging into my equations to solve for my other variables. So taking z equals 3, I could plug it into equation 4 or 5. I'm going to choose 4 because it's a little simpler. So x plus 3 is equal to 4. Solving for x by subtracting 3 to both sides, we get x is equal to 1. Then once I know what z is equal and I know what x is equal to, I can plug into any of my three original equations to solve for y. I'm going to plug into equation 1. I think it's the simplest. So x plus y plus 2z equals 3 is going to become 1 plus y plus 2 times 3 is equal to 3. Solving that out, 1 and 6 makes 7. Subtracting 7 from both sides, we would get that y is equal to -4. So I have x is equal to 1, z is equal to 3, and y is equal to -4. You can write your solutions just like that, or you can write them as this combined solution set x comma y comma z. Now, once we have our solution, the last thing we always want to do is we want to make sure we are going back and we're checking to make sure everything is correct. So I can plug those x, y, and z values back into all three of my equations. And as long as they all come out to that correct constant or solution at the end, then I know I did everything correctly. If I get anything incorrect or any solutions that don't work, then that means somewhere in my tracking and my adding and subtracting, I probably made some sort of an error. Okay, so I know it's a lot, but just to kind of help you keep everything straight, compartmentalize everything, some easy steps to follow. The first thing we want to do is we want to eliminate one of the three variables by adding those two different equations together. So if we have those three variable equations, A, B, and C, then we're going to add, for instance, the first two together to get D and the second two together to get E. So we end up with two variable equations. It doesn't necessarily have to be first and second and third. It could be first and second and first and third, or first and third and second and third. It's just what's going to work to get those variables to cancel out. Okay, once I have those two variable equations, I'm going to treat as another set, and I'm going to add those two equations together to eliminate a second variable and be able to solve for that single remaining variable. So if I add D and E together, I should get that single variable equation. And then once I have that single variable, I can plug back in to solve for the other variable, and then plug those two back in to solve for that third one. And of course, once I have all three solutions, I want to plug it back into my full system so I can check our work and make sure that we are good to go. Okay, so it's a lot of talking about what to do. Let's actually put it into practice. So let's look at example 1. We have negative x minus 5y minus 5z is equal to 2. 4x minus 5y plus 4z is equal to 19. And x plus 5y minus z is equal to negative 20. And I'm going to go ahead right off the bat, before I do anything else, I'm going to label the equation A, equation B, and equation C. And this is just to help us keep track of our equations, make sure we don't lose them as we start to get more equations when we eliminate. So we want to look for something that's going to cancel out. X and negative x could cancel out. 5y and negative 5y could cancel out. The z's aren't going to really help us, but definitely those x's or those y's. Let's do the y's, because I have that negative 5y and positive 5y right there next to each other. Keep it nice and simple. So let's take those first two equations right here, and we are going to add them together. So 4x plus x will give me 5x. Negative 5y and 5y are going to cancel out. 4z minus z would give me 3z. And then that would be equal to 19, and negative 20 would, of course, make negative 1. And we're going to go ahead and label this equation D, because it's now my fourth equation. And notice it has two variables. So for whatever our next set is, once again, we're going to want to eliminate y. So our equation E, our fifth equation, once again, only involves x and z. So we used equation 2 and 3. For our next one, let's use equation 1 and 2. We have negative 5y and negative 5y. I know that those aren't going to cancel out right away. We're going to have to subtract instead of add. But the reason why I want to do equations A and B instead of equations A and C is because if I do A and C, I'll get the y's and the x's to cancel out, which will leave me with just z in my equation, which is not what I want. Okay, I know that seems like that'd be great because I'd only have one variable, but unfortunately it actually ends up making your answers a little bit incorrect. So let's do equations A and B. So I'm going to rewrite both of those equations for us. So we have negative x minus 5y minus 5z is equal to 2, and 4x minus 5y plus 4z is equal to 19. And just to help us keep track, that is, of course, equation A and equation B. And we are going to be subtracting these two equations, because if I subtract the two equations, then I'm going to get those y's to cancel out. So negative 4x minus 4x would give me negative 5x. Negative 5y minus negative 5y is the same as adding, so that's going to get those to cancel out. And then negative 5z minus 4z would give me negative 9z. And then 2 minus 19 would give me negative 17. In this new equation, we're going to go ahead and label equation E. Okay, so if I did my job, my new equations D and E should both only involve two variables in the same two variables. So 5x plus 3z equals negative 1, and negative 5x minus 9z equals negative 17. So same two variables and only those two variables. So now I'm going to take those two equations and I'm going to add them together, but I do want to check before I add them together that I don't need to multiply anything. So 5x plus 3z equals negative 1, and negative 5x minus 9z equals negative 17. And by complete luck, our 5x and our negative 5x are going to cancel out right away, so I don't have to worry about multiplying either of those. Sometimes that works out. Sometimes you might have to multiply by something. That's just how elimination works. And once again, just to make sure we're not losing track, this is equation D and equation E. Adding these across, 5x and negative 5x, that's going to cancel out. 3z and negative 9z is going to give us negative 6z. And negative 1 and negative 17 is going to give us negative 18. Okay, so we've now added our two sets of our 3x3s and then our set of our 2x2s, which leaves us with a single variable with a single constant. So now I can just solve for z, so dividing both sides by negative 6. We get that z is equal to 6, and negatives are going to cancel out. Negatives are going to cancel out over here. So we get that z is equal to 3. Now that I know what z is equal to, I can back plug to find the rest. So if z is equal to 3, I can plug that into either of my two equations. I'm going to plug it into equation D. So 5x plus 3 times 3 is equal to negative 1, which means 5x plus 9 is equal to negative 1. Minusing 9 and minusing 9, we get that 5x is equal to negative 10. Because, of course, our 9s are going to cancel out. And then dividing both sides by 5, we get that x is equal to negative 2. And then last but not least, once we know what z is and we know what x is, we can plug into any of our equations to solve for those. I'm going to plug into equation 3 because it has just a single x and a single z, so I think that's going to make things a little bit easier. So plugging into equation 3, we get that negative 2 plus 5y minus 3 is equal to negative 20. Looking across, I don't have anything I need to multiply, so I'm going to add 2 to both sides. And I'm going to add 3 to both sides. That's going to get 2 and 3 to cancel out. Over there on the right, negative 20 plus 2 plus 3, that's the same as negative 20 plus 5, which would give me negative 15. So 5y is equal to negative 15. Dividing both sides by 5, we get that y is equal to negative 3. Okay, so I know what z is equal to, 3. I know what x is equal to, negative 2. I know what y is equal to, negative 3. So now from here, I just want to plug into all 3 of my equations. So I'm going to plug x in, I'm going to plug y in, and I'm going to plug z in. If you want to try and do this checking step on your own, you can go in and pause and try and check. If you want to follow along with me, you can. So plugging into our first equation A, we get negative 2 minus 5 times negative 3 minus 5 times 3 equals 2. Then plugging into equation B, we get 4 times negative 2 minus 5 times negative 3 plus 4 times 3 should equal 19. And then last but not least, negative 2 plus 5 times negative 3 minus 3 is equal to negative 20. Now let's check each one of these, make sure we're good to go. So negative times negative 2 is 2. This negative 5 and negative 3 and negative 5 and positive 3, that's going to cancel out. So that one does equal 2. Here, 4 times negative 2 is negative 8. Negative 5 times negative 3 is positive 15. Negative 8 plus 15 would be 7. And then 7 plus 12 would equal 19. And then negative 2 and negative 3 would be negative 5. Negative 5 plus negative 15 does equal negative 20. So since everything worked all the way across, our solutions here at the end, of course, will be our 3 different solutions that we got. So y is equal to negative 3, x is equal to negative 2, and z is equal to 3, which of course we can also write as that combined point of x value first, so negative 2, then y value, negative 3, and then z value of 3. Either way would be fine for us to write our final answer. Okay, so the big thing with 3x3s, y'all, they're not super crazy, but they are long. I mean, I think we did 1, 2, 3, 4, 5, 6, 7, 8, 9. I mean, 10 plus steps to get all the way through that. So you just kind of have to plug and chug away. Be really careful with your numbers and your math and make sure you're doing everything correctly. I want you to go ahead and do number 2 without me. So go ahead and pause the video and try number 2. Same thing, label your equations and just take your time as you're working through this one. All right, y'all, let's talk through number 2. Make sure we're all on the same page. So we got equation A, B, and C. I went ahead and added those equations B and C. It's going to get that negative 5y and positive 5y to cancel out. Leaves us with negative 3x plus 2z equals negative 5. Then adding A and B together, I can subtract B, which is going to get that negative 5 and positive 5y to cancel out. Once again, leaving me with 4x minus 4z equals 12. Okay, then adding D and E together, we don't have any matching x's and z's, but I can multiply that equation D by 2, which will give me positive 4z. So adding those two equations together will get z to cancel out and leave us with negative 2x is equal to 2. Dividing by negative 2 on both sides, we do get x is equal to negative 1. Once I know what x is, I can plug it back into either of the two equations. I chose to plug it back into equation E. So 4 times negative 1 minus 4z equals 12, which gives me negative 4 minus 4z equals 12. Adding 4 to both sides and then dividing by negative 4, we get that z is equal to negative 4. And then once I have x and z, I can plug it back into any of the three equations. I chose to plug it back into equation A. So negative 1 minus 5y plus negative 4 is equal to 17. Subtracting by negative 1 or subtracting by 1 and adding by 4, that gives us negative 5y is equal to 20. Dividing by negative 5 on both sides, we get y is equal to negative 4. Once we have those three answers, of course, we want to go ahead and plug in all the way across and check. And we can see that we get the same answers all the way through. So x is equal to negative 1, y is equal to negative 4, and z is equal to negative 4. Okay. If you have more questions about that one, y'all, the biggest thing with 3x3s is just practice, practice, practice. These are difficult. They're time consuming. So don't feel like you need to be perfect at them right away. Okay. Let's go ahead and pivot a little bit, and we're going to talk number 3. Number 3 is a word problem. And the big thing with these word problems, sometimes you'll have to solve them, sometimes you won't, but a lot of times you have to decide your own variables. So let's look at number 3. You have a combination of nickels, dimes, and quarters that totals $2.75. There are 21 coins in total. The number of dimes is twice the number of nickels. So we want to set up a system of equations to determine how many nickels, dimes, and quarters you have. And we are not going to be solving this one. We're just going to be writing it. Okay. So first and foremost, we want to decide our variables. You can use x, y, and z, but sometimes with things like this, y'all, I like to use variables that make sense. So let's instead use N for nickels, D for dimes, and Q for quarters. Okay, and the first piece of information they gave us is that nickels, dimes, and quarters total up to make $2.75. So I need to add all of my nickels, dimes, and quarters together to get that total cost. But I don't need just the number of nickels, dimes, and quarters. I need the actual value of those nickels, dimes, and quarters. So nickels are worth 5 cents. So I want 0.05 nickels. Dimes are worth 10 cents, so plus 0.1 dimes. And then quarters are worth 25 cents, so plus 0.25 times the number of quarters. And that should equal our total of $2.75. Okay, so that's our first piece. That is equation 1 that we got. Okay, then our second piece of information is that there are 21 total coins. And of course, my stylus decides to go up. So if there's 21 coins in total, this time I don't need the cost or the value of each coin. I just need the number of coins. So if I only need the number of coins, then this time I can just add nickels, dimes, and quarters together for my second equation. So the number of nickels plus the number of dimes plus the number of quarters equals a total of 21 coins. So a little difference. First one is the cost of all the coins equals my total value. And then equation 2 is just the number of coins. So nickels plus dimes plus quarters equals the total number of coins. Then they gave us just enough information to write a third and final equation, and that is that the number of dimes is twice the number of nickels, and that's going to make up our third equation. So if dimes is equal to twice the number of nickels, then for my third equation, my variable D is equal to 2 times my variable N, because dimes is equal to twice the number of nickels. Okay. Now, of course, if I wanted to, I could solve this one out. I might want to manipulate and work that third equation so I get dimes and nickels on the same side. So I could actually do my 3x3 steps, but we don't have to solve this one. We are just trying to write that equation. And that's really all there is to it. They're usually pretty intuitive, and we'll practice this a little bit more in the coming days. Okay, but that is all there is to it, y'all, for systems of 3 equations. They really just take practice. So do lots and lots of practice. Take lots and lots of time on these, y'all. The more you do them, the better you're going to get at it.